Hello, everyone. As promised, finally, I'm going to start my new playlist about PLCs or programmable logic controllers because this semester I'm basically teaching a course about it on our campus. So I said, now that I'm dealing with PLCs, let me make some lectures about PLCs and put it on the channel for the people who are interested. So, I'm gonna post more videos. This is my first one, and uh, hopefully, you're gonna see the theoretical part, the practical part. In future videos, you're gonna see me working with actual Siemens PLCs, and I might also ask my students to help me put some lectures together too, as they are involved in this dealing with this hardware. So what is a PLC or a programmable logic controller? This is basically what you see in industry. If you look at many of the control boards in oil industry, in petrochemicals, in pharmaceutical companies, in CNC machines, anywhere automation is needed, robots and so on, the controller, the brain, the computer that is controlling the behavior of the system is something like this. You don't see an Arduino or a Raspberry Pi or something, right? Those are good for learning and hobby. For industry level control, you want something that is rugged, is robust, you can count on it. It has lots of input and output modules. You can program it in different ways, including some simple ways that does not necessarily need a deep knowledge of programming and so on. So this is what the industry is typically using, called the PLC, or programmable logic controller. So it's really a digital computer for industrial automation and so on. Now, I don't want to get into history of that, but first they were developed in the automobile manufacturing industry, and I guess Dick Morley is mostly credited as being the father or the inventor of the first PLC, the Modicon, and he did it for General Motors in 1968, so a little bit short of 60 years ago, 57 years ago or something. So the PLCs have been around for close to 6 decades now, and they started in automotive industry, but now they are all over the industry and everywhere. What are the key features of a PLC? First, of course, they are programmable. That's the first thing. They have to be programmable. They are a controller. Okay, that is absolutely important. The bigger thing is they should be rugged. They should be made to withstand conditions that are not typically when you are a hobbyist or somebody who's just trying to learn in a control environment. You will never expose your control board to any of those, like very high or low temperatures, like vibrations, like dust and so on. They should be enclosed enough. They should be basically tolerating all of these extreme conditions, and you want them to operate in real time. Okay, when a robot is doing some assembly or pick and place, when something in a automated conveyor or manufacturing line, like a medication or I don't know, a car part or anything, or oil and tanks and all of those things are being controlled, their volumes, their speeds, their motions and so on, you cannot afford to have non-real time. You cannot have your controller make a decision maybe once every minute or 5 minutes or 2 minutes or something. They have to make very fast decisions. For that reason, the programming language that we typically use for them is relatively simple, and we prefer to use simple programming languages, that is in our next video, like ladder logic and so on, to make very fast decisions. Okay, so we want them to do very fast decisions. Now, what are the components of a common PLC? The first one is the brain, the computer, or the central processing unit. which is where your algorithms, control algorithms, will be uploaded to. It receives the inputs that could be up here, they could be down there for a Siemens PLC, and it has also allocated input-output modules. It receives this digital inputs, digital or analog inputs also, so it can receive digital and analog inputs, and then it can also send out the digital outputs and the analog outputs. So for digital we use D, for analog we use A, for input we use I, and for output we use Q, not O. Okay, so it can receive inputs and outputs. The programs are all inside of it. It makes the decisions. It has it can have its own place for Ethernet connection, but mostly there are allocated I/O modules and communication modules that bring in fast, reliable connections beyond just simple wires like Ethernet and so on. So we're going to talk about it. Also, inside this brain there is memory. Okay, so you have memory here as well. And the memory, of course, there is the working memory or RAM, there is ROM, that is for permanent storage and so on. So you know about that, I don't want to take your time, but there are both types of memory on these brains. Then, and by the way, these pictures that I'm showing, these are for Siemens. These are for Siemens PLCs. And this PLC that I'm going to talk about is called S7-1200. This is the one that I will be using in future videos. This is one of the common Siemens PLCs. There are newer versions of that. There are older or smaller versions of this. This is kind of mid-range PLC that we're going to use in our class as well. So Siemens is one of the manufacturers. There are lots of other ones, but Siemens is the most famous, the biggest manufacturer of PLCs. And so we're going to see pictures right now of Siemens components. So if we go down, then as I said, there are allocated I/O or input-output modules beyond just the PC. So you can have modules like this that are for digital and analog input-output. And many of them, typically this block here will go right there. So as I'll show you in one of my future lectures, this top portion here, this part, there are pins here and there, and you can even take the whole thing off. The same thing goes for here. Okay, these are where those pins for input outputs are. Also, this panel here in the middle, this guy, you can take it off. It's a placeholder, and then these devoted I/O modules will go and place there, and you can bring in more input outputs. Okay, now most of the PLCs are not running on your 110 volts that is coming directly out of the wall. So most of the PLCs are not working on AC, and they are not working on 110 volt AC. Most of them, including the Siemens, are working on DC voltages, and in the case of Siemens, it is mostly working on 24 volt DC or direct current. So this wall current should go into this power supply, and 24 volt DC should come out. That can be sent to the central processing unit or CPU. Okay, so you need to have this guy, and you need to plug this one into the wall, not directly the PLC, of course. There are communication modules. This is where the Ethernet cable goes, and there are other communications beyond just wires for input-output. So most of the time, the Ethernet plugins are going to go into this, and there are other basically modes of communication. And the Ethernet that is used for Siemens is called the Profinet, and we're going to talk about it. Okay, so there is Profinet, which is the internet specific to Siemens, and there are also these modules called Profibus, and this is another older basically mode of communication, although it is still used. So we're going to talk about these, and they can come and bring the information digitally into these pins and basically do the I/O. So this is communication module, I/O module, power supply, and the brain. Now, of course, there is another component, and that is human machine interface, or HMI. So HMIs are monitors with input buttons or touch buttons here. And typically this screen is not always, sometimes you might see somewhere that this is touch, but most of the time they are being dealt with these buttons. And this is for the human to interact with the system, okay? Especially for operators. So if the operators want to change something or control something, or, do some basic modifications, they typically do it through these monitors, because the operators most of the time are not writing the control algorithms. The control algorithms are written in different languages, as I said, like ladder logic, function block diagrams, and so on. And through the Siemens software, which Simatech, if I'm pronouncing it correctly, through this software, you can connect to the PLC and upload your program, okay? And we're gonna look at all of this. But an operator typically does not change those basic programs and just work through these to do some basic modifications and so on and interact with the PLC. So there is also human machine interface, or HMIs. Now, you might say, well, why won't you just use, let's say, relay-based systems or microcontrollers to do the control job? Why would you use these PLCs? So let's briefly talk about that. So first of all, you know that PLCs are like the replacement for the relay-based systems. In relay-based systems, which many of the control boards in the past used, basically a bunch of relays, a bunch of switches, and so on, were used to send some inputs and outputs based on different conditions. And those relay systems were specifically designed for the task at hand. So if you have to do something different with the same control board, you couldn't easily do that. You had to do lots of rewiring and a lot of modification to be able to use those relay systems. So compared to relay systems, PLCs are versatile. They can be programmed for anything. So that is advantage of them over relays, not microcontrollers, because microcontrollers, you can program them to do similar things. But relays are basically more task specific when you design them. Now, the other thing is they are relatively compact designs. So you see that in these few components that you have the brain, you have all the input output, you have the power supply, you have anything that you need. And HMI does not need to be always right next to the PLC. Even many projects might not necessarily have HMI if there is no need for operator to basically tamper with the system. So, and all of these typically, as we'll see, will be mounted on a rail, which we'll see is called the DIN rail. And this DIN rail is basically a metal rail, and it goes right here into this slot. As you can see it here and here. That slot is in the back of all of these components. So all of them will be mounted right next to each other on a rail, and they are only going to occupy a small space. So this is what I'm talking about. There is this rail in the back, and then you mount the power supply if you need an Ethernet switch, if you need a communication module. This is the brain signal board, I/O separated module, and you can add as many I/O modules as you want. The design is modular. So depending on how many input outputs you need, you can add more and more of these modules, okay? So you put them all on a rail, and this is, as I said, is going to only occupy a small space, and so this is really compact. The other thing they have compared to relays and sometimes microcontrollers is they are, as we said, very fast and real time. The better part is reliability and ruggedness, as we said. They are really good. Now here in this top part, I'm just comparing them to relays, but in the bottom part, we're going to compare them to microcontrollers. So of course, compared to even relays, of course, they are more reliable. They don't have so many mechanical parts like the relays do, and so they are more reliable for persistent operation. Now, diagnostic and troubleshooting is something that is much, much better compared to relays. So if something is not working, they have lots, especially like Siemens, they have tons of built-in diagnostics. So you can easily find where the error is, the bug is, and you can easily go ahead and fix it. In relays, you cannot do such a thing easily. Then integration, of course. So we said you can integrate them with HMIs, you can integrate them with systems like SCADA, which is, if we have time, we'll talk about it in a separate lecture, supervisory control and data acquisition systems and so on. So they are really can be integrated with other systems, and they are scalable and modular. Okay. So you can easily add, as I said, as many modules as you want and use them for bigger and bigger projects. Now, compared to microcontrollers like Arduinos and so on, what are their advantages? The first one that we said, they are rugged. They can withstand harsh environments. That is the main thing for industry. Their programming could be easy because if you want to program them like an Arduino, you have to write C. Raspberry Pi, you have to write Python and some other languages. And not everybody is really the best in programming these. Now, of course, these days with the use of AI platforms, many people can use them to write programs, but it doesn't mean necessarily that they can debug it if they are not working and they can understand it. So you cannot 100% just rely on these platforms. You have to know that programming language a little bit yourself too. But a ladder logic that we're going to see next in the next lecture is, or the next two lectures, is a very easy, understandable logic that anybody without prior programming experience can understand and even can program. Okay? Now they have built-in I/O modules. As you saw, they have built-in, not only the CPU has built-in modules, you can add as many modules as you want for all sorts of industrial sensors and actuators. But for microcontrollers, many of them, you cannot easily just do it with a simple Arduino. Many times you need these shields, right? And you need PCBs and make shields to, let's say, interface an Arduino with, let's say, a motor or an RPi with a camera or something. So you need all sorts of shields for all sorts of sensors and actuators. But these guys already have those I/O modules. Real-time performance, we talked about it. Okay, they are fast, they are scalable, and they are modular. We talked about that. They are easy in diagnostics. Of course, microcontrollers could be easy too. They have support, industrial support for protocols and communications, and of course, safety and compliance. The basically, if I want to say it, the rigor of the design for safety and compliance on PLCs, the standard is much higher than a simple Arduino. They are really made to be safe, be around people, and many of them, they have fail-safe modes, okay? So if the signal that is supposed to go out doesn't go out, still they can manage the control system so that, for instance, the robot does not crash anything and so on. Many microcontrollers don't have fail-safe modes or anything redundant to control unforeseen circumstances. Okay? Now, of course, they are used, as I said, all over the industry, from manufacturing, from process industries like oil and gas, chemicals, pharmaceuticals, water treatment, and so on, from building automations like HVACs, elevators, lighting, in transportations like the traffic signals, railway systems. In the energy sector, they are used, and also they are also used in agriculture, like greenhouses, irrigations, and so on and so forth, for large scale systems, of course. So they are really the main controllers of the industry. Now, the final thing for this short lecture is, what are some very common, well-known, famous brands of PLCs? As I said, the big guy, the biggest guy, I would say, all over the world, if you consider entire world, is Siemens. Siemens is the German company. It has headquarters and places all over the world, including United States, and they are really known for being high performance. They are really good. They have a wide range of options. They are not cheap also, and their S7 series are very popular. We talk about different models of them later. But Siemens overall, I can say, is the biggest player. In North America, including US, the other big player is the Rockwell Automation, and they are also known by Allen Bradley PLCs. Okay, they are user friendly, they are very popular in North America, and as I said, and their series that are very common are control logics and compact logics. Okay, and so this is how they look like, these Allen Bradleys. These two are like the biggest guys. Then of course we have Mitsubishi, okay, which are relatively affordable too, and they are common in manufacturing and machine control. We have the Omron, which are compact designs, and if you need advanced motion control, they can be good, like the Sysmac series is one of those. Then we have ABB, which have their high quality PLCs, and one famous series is AC500. And then finally we have the Schneider Electric, who bought basically the Modicon series. Remember, I said these were the first PLCs that were designed 6 decades ago in the US for General Motors, and then this company was bought by the Schneider Electric, another German company. So they have been around, and their Modicon series have been recognized all over the world, and this is basically one of their PLCs. So if you see stuff like this, or this, these are the PLCs that you will see all over the industry. Now, many times you might not directly see them because they are typically in these control boxes. Okay, they are kept inside the control boxes. And the only thing of these systems that you might see outside are these HMIs. Typically, you only see these guys out. The PLCs, those brains, are inside the control boxes or inside the big machinery, and you might not see directly this one. But the goal of this class that I have on our campus, and hopefully these online lectures, is to show you behind the scene how to communicate with them, how to program them, and how to use them for different applications. So hopefully this very first video was useful to you, and I'm gonna see you in the next lecture. Thank you.